Welcome again, everyone, and thank you for participating in today's online event. We see that there is participation from across Canada, which is great. The title for today's presentation is Mechanisms of the Impact of Pollution on Brain Function, and we will be presented by Dr. John Malott. Dr. Malott has been practicing environmental medicine for more than 30 years. He has assessed more than 12,000 people for possible environmental links to chronic medical conditions, including multiple chemical sensitivity. He has developed and provided workshops for continuing medical education for both the Canadian and the Ontario Colleges of Family Physicians regarding sick building syndrome, multiple chemical sensitivity, chronic fatigue, and fibromyalgia. He was appointed by the Ontario Minister of Health and Long-Term Care as a clinician expert to the Ontario Task Force on Environmental Health 2016 to 2018, which made recommendations to help improve the understanding and the recognition of environmental health conditions such as chronic fatigue syndrome, fibromyalgia, and MCS.
Anyway, thank you all for attending. I have to tell you, I have a lot of information in this presentation, and everything that I have to say that I present is found in the medical literature and could be cited. I hope that there are three things that you'll get out of this presentation. The first is to understand how pollution impacts on the brain, what the biology is. Be able to recognize the overlap in the mechanisms for diseases like neurodegeneration and multiple chemical sensitivity. And the third is to become more familiar with the scientific evidence for the existence of MCS as a distinct biological condition. We'll start with what you probably already know, that there's 86,000 new chemicals that have been introduced into the environment since World War II. 41,000 of them are in commercial use. And between 500 and 1,000 new chemicals are introduced to the environment every year. Some of them, 3,300 of them, are labeled as high production, which means that there's at least 500,000 kilograms per year being produced. These chemicals are swimming around the planet. They get into the air. They end up in the water system. They end up in the food chain. We sit at the top of the food chain and we eat these chemicals. They're in the outdoor air. They contaminate our indoor air. And then there's human behavior, the things that we do to increase our own exposures, the kind of products we use to build our buildings, to clean them on a daily or semi-daily basis, and the personal care products that we apply all the time. And as a result, everybody is contaminated with chemicals. The average North American, depending on the study, has up to 200 chemicals stored in their body. Some of these chemicals will detoxify slowly, so they're hard to get rid of. Some of them we can detoxify fairly quickly, but we keep having exposure to them. Example is plastics. And most of them are lipophilic, and what that word means is that they are absorbed easily by fats and oils. They're not water soluble, they're oil soluble. Examples of where these can be in our body are cell membranes, and in particular the brain, which has a very high fat and oil content. So we have what's called a body burden, which is the chemicals stored in our body. And you can see from this list, it's huge. All different kinds of sources of chemicals that are stored in our body, based from fossil fuel burning outside to the building materials in our food, such as pesticides, etc. The list is huge. The United Nations World Health Organization 2 years ago, they stated that there is a fifth risk factor for non-communicable diseases, chronic diseases that we have that aren't infectious, and they named it air pollution. So the major pollutants outdoors are particulate matter and ozone. It also includes nitrous oxides, sulfur oxides, carbon monoxide, but the major ones are particulate matter. The exposures that we have fluctuate, goes up and down, but it's continuous, more or less, all the time. And the influence of these different pollutants could be additive. It could be synergistic, meaning that each one can make the other one worse. Particulate matter is particles in the air. It could be particles of liquid, but they're considered to be solid because they can be measured as a distinct object. They can be made of all kinds of things. The most common source of them outside is a byproduct of burning fossil fuels. So we get those things from traffic and so on. There are three categories based on the size. So there's coarse, which, as you can see, is ranges from 2.5 to 10 microns. There's fine, which is 2.5 microns or less. And then there's ultrafine, which is below 0.1 microns. We consider those nanoparticles. And you can see an idea of what 1 micron is. It's about 1/1000th of a millimeter. So this is just an image which gives you an idea. You can see that the size of a cell is around 5 microns. Around 1 micron is bacteria. When we get down to about 0.1 microns, that's a virus. Viruses obviously are in the news today, and we're all concerned about how easily they can get into our bodies just by being inhaled. And then there's things below that. So you get an idea of how small the particles are that are in the air that we're breathing on a regular basis. So when it comes to air pollution and we look at the effects on health, we know that there are adverse effects at the current levels of exposure that we have in the Western world. There's many studies showing adverse effects that are associated with just living close to major roadways. There isn't really a recognized threshold for health effects. And what this means is we don't know how low is safe. And it doesn't matter whether the exposure is indoors or outdoors. The ultrafine particles, the little tiny ones, small, like the size of a virus and smaller, they have a negligible mass, which means they don't weigh very much, but they are the main contributor to the total number of particles in the air that we're breathing on a regular basis. They're 80 to 90% of all those particles. And when you see at the bottom there, a concentration right close to a major roadway can be as high as 48,000 per cubic centimeter. And in the rural environment, maybe only 2,600. So it's huge. So when we look at that 48,000, if you're near a major roadway, and you realize that the average volume of breath is 500 cubic centimeters, that when you're near a major roadway, you're taking in 24 million ultrafine particles per breath. And then look, 16 breaths per minute, 960 breaths per hour, 23,040 breaths per day. You're inhaling an awful lot of very fine particulates. So most of the studies of air pollution which look at an association of risk of developing chronic disease with outdoor air pollution are considering the effects of long-term exposure. It's insidious. It goes on and on and on. And we spend more than 90% of our time indoors. 70% of the time is spent at home. So the building envelope acts as a filter, and it may reduce the exposures that we have somewhat, but we're still exposed to the indoor air pollution, the outdoor air pollution when we're indoors. An example is about 65% of the particulate matter from outdoors is actually inhaled in your house. So we don't know what the recognized threshold for health effects is for the outdoor particulate matter. And it's regardless of whether we're indoors and outdoors. The studies of long-term exposure have to recognize that most of our exposures are actually occurring indoors, even at the current levels of exposure. And as I've said already, many studies have demonstrated adverse health effects associated with residing in proximity to major roadways. There's a difference with the amount of exposure. So what we also have in indoor air pollution are volatile organic compounds. So what this means is volatile means that substance exists in a vapor or a gas phase at room temperature. An organic means that carbon is part of the molecular structure. It doesn't mean that it's pesticide free. Um, so the total VOC concentrations indoors are 4 times higher than outdoors. And the source of these compounds are generated from the indoor environment. Household products, air fresheners, fragrances, building materials. When the building is new, we have even higher levels indoors than after they've off-gassed for a while. The semi-volatile organic compounds are inhaled, usually attached to particles, although they can be in the air as well. And because they're on the tiny, tiny particles, they tend to penetrate deeper into the respiratory tract, right down deep in the lungs where the carbon dioxide and oxygen transfer takes place. And they interact with the cells of the bronchial tubes and lungs as they sit in contact. So the burden of disease from air pollution is due to the joint effects of indoor and outdoor sources. There's potential for any organ system to be impacted by the fact that these things can be absorbed and how we respond to them. But the focus of this review is going to be the impact on the central nervous system. So to understand the exposures, start by understanding that there's something called the blood-brain barrier. And its purpose is to protect the brain from things that don't belong in there. It's actually in the capillaries, and capillaries are the smallest blood vessels. This is where exchange takes place with oxygen, carbon dioxide, nutrients, etc. They're very, very tiny. They're very, very thin. But in the brain, these cells are very tightly joined together to provide this effective barrier. And the cells are programmed to be very restrictive in what they will actually transport across them into the brain. But they can more easily transport chemicals that are soluble in oil, those lipophilic chemicals that we mentioned earlier. Examples of things that are like that can get into the brain easily are alcohol, some drugs like cannabis, volatile organic compounds, and semi-volatile organic compounds, although we're not so sure how well they can traverse this system. There are 12 nerves called cranial nerves that come directly from the brain rather than from the spine that do various things. And we're taking a special interest tonight in 2 of them. One is the olfactory nerve, which senses and discriminates smells. So you can describe what something smells like. It's actually the shortest nerve that goes directly into the brain. And then there's a trigeminal nerve, which transmits sensations from your eyes, nose, and the skin of your face. So when something tickles your nose, you don't smell it, you sense the sensation. That's the trigeminal nerve. These 2 nerves mutually interact with each other. They both have nerve endings in the mucous membrane lining the nasal cavity. The nerve endings are very close to the surface. And these are the only routes by which the brain is actually connected to the outside environment. So the importance of this external exposure is that they can facilitate a process called translocation. So although a large fraction of these particles that I've described to you are removed by getting caught in the mucous membrane of the nose, lined with mucus tends to move and be replaced, and we get rid of things that are trapped in there. And then we've got immune cells swarming around there as well, engulfing and digesting and getting rid of the things that are trapped in there. However, it's less than perfect. And especially the ultrafine particles can reach the brain directly by this process of translocation. What happens is they go through the lining of the nasal cavity, they get into the olfactory nervous system, and these neurons pass through the skull right into the brain, and it provides a barrier from the nose directly to the brain to deliver these particles, and it bypasses the blood-brain barrier. These little tiny particles, ultrafine particles, are also better able to enter cells because they're so small. and they exert toxic effects relative to their size because they have a large surface area, even though they're very, very, very light. And stuck to them are toxins like SVOCs, heavy metals, etc. So this slide just gives you a summary of what we've just stated, that we've got the ultrafine particles and slightly larger ones, the PM2.5. They get into the respiratory system, they're systemically absorbed, they're partially stopped by the blood-brain barrier, or they can be translocated directly from the nasal cavity via the olfactory nerve or the trigeminal nerve. They get directly into the brain. And this constant exposure over time can affect the number and the function of the cells of the brain. Humans are made of cells, 3 trillion cells. The brain itself has 100 billion cells called neurons, and there's other kinds as well. The cell is the smallest unit of life. It's what keeps us alive. That's what we are. The cell needs to absorb oxygen, absorb food, convert food and oxygen into energy, needs to have enough energy every day to perform its job description, whether it's to produce something or just to be a bone cell and be a support system. It needs to communicate with the other cells. It needs to get along with the other cells. It can't be irritable and overreact. It can't be depressed and underreact. It needs to be able to reproduce, and it needs to be able to eliminate its waste products. And that's a process called detoxification. So this is a cell. Those of you who ever took biology will remember some or all of these things. It's not important to remember what I just labeled there, but just to give you an idea of how many different things there are in the cell working together to make the cell function. So to try and describe that, I came up with this metaphor that the cell is like an independent nation. It has a defined landmass, so cytoplasm. It has a border and immigration system. These are the cell membranes which guard the entry into the cell. It has a constitution, the DNA. It has a benevolent dictatorship. The dictatorship rules and regulates according to the DNA, the nucleus, according to the constitution. It has a judicial system. So it interprets and applies the laws of the constitution in the DNA and makes those things happen. It has a police system which screens for things like misfolded proteins and corrects them or eliminates them. And it has a manufacturing industry. So it has factories that make proteins. And it has factories for making lipids. These are the fats that we use, for example, to build cell membranes. And there's more. Trade and commerce. It exports things that it makes and sends them to other cells. It has to import things from other cells, imports materials used for energy production, like starch and fat. It has a transportation system. Things actually move around inside the cells, being sent to various organelles to provide whatever equipment is required. It has an energy sector to produce, store, and deliver the energy wherever it's needed. Those are the mitochondria that we may mention later on. It has a foreign affairs, so it can release messengers to neighboring cells to let them know what's going on. A communication system to hear what the other cells have to say. Those are receptors. We're going to talk about those. And then there's waste management. It has a system for detoxification. It has to be able to transport waste and dump it outside the cell if it can't get rid of it or reuse it. So in order to get rid of the garbage that's produced, or contaminates the cell has a detoxification system. It's a molecular waste disposal. So on the one hand, we have toxins that are called oxidants or free radicals, reactive oxygen, nitrogen species. These are all different toxic molecules, but we have a system in place where we use antioxidants to neutralize those toxins. And when we do a good job, we have a healthy, balanced detoxification system. So pollution tips the balance. The balance can come from, number 3 there, excess exposures, but it can also come from deficient nutritional support or an abnormal genotype. Perhaps you're just born with a less than adequate detoxification system. And when this happens, there are changes that occur in the cells that we can actually measure. And we call those changes oxidative stress. When oxidative stress occurs, it causes damage to neighboring molecules. These are the lipids, those fats and oils. It causes damage to proteins. It causes damage to nucleic acids. And these are the parts of your DNA. And so as a result, we will see damage, receptors on the membrane, to the mitochondria, which are the particles or organelles, inside the cell that produce the energy. Or we see damage to the DNA or what's called the epigenome. And the epigenome is the covering of the DNA, which when it's not present, the genes in that DNA are active. And so we cover some of our genes so that they're not active. If we damage the epigenome, we damage DNA functioning. And so when there's enough oxidative stress, we see systemic inflammation in the body. We see damage to tissues, and we see organs starting to dysfunction. So oxidative stress is particularly a problem in the brain. The brain is especially vulnerable to it because it has naturally high oxygen requirements. And so therefore we get more of what's called those reactive oxygen species produced. And it's also very high in what are called polyunsaturated fatty acids. And these are the fats and oils that we were talking about before. They're easily oxidized. They're easily affected by these reactive oxygen species. The long-term exposure to oxidative stress in the brain has a causal role in a range of pathologies that occur within the brain. And it is a key component of neurotoxicity. So the pollution exposure that we get over time induces the oxidative stress, which can lead to dysfunction in the mitochondria, dysfunction in the production of energy, and it can lead to subsequent neurodegeneration. The cells don't have enough energy and they die. There's also an association of these pollution exposures with the neurodegenerative disorders in the literature. So we actually see these pollution exposures causing oxidative stress and resulting in diseases like Alzheimer's or Parkinson's disease. Oxidative stress is always associated with systemic inflammation. And what that means is that the messengers of inflammation, the chemicals that are telling the immune system to respond, to do something, are circulating around in the body. And there's a scientific consensus that these two mechanisms are entwined with each other. They both play a key role trying to mediate the hazard effects of environmental stressors. They play a key role in the development and progression of neurodegenerative disorders. And the most prominent effects caused by air pollution in both humans and animals are both oxidative stress and neuroinflammation from systemic inflammation. The studies of particulate matter exposure repeatedly show changes in these markers for inflammation and oxidative stress, whether the studies are cell cultures, animal models, or in human patients. So what do we see? We see reductions in brain mass because of cell loss, even at exposure levels below what we presently have as the upper limits of safety. There's reductions in particular areas of the brain called the hippocampus, the thalamus, the prefrontal cortex, and these reductions are associated with exposure to particulate matter. Studies in the United Kingdom of looking at people living close to major roadways, we see these same reductions, more likely. We also see olfactory dysfunction. And what that means is we start to see deficits in the ability to identify an odor and detect it. And these things can occur years before the motor symptoms or cognitive decline that we see in neurodegeneration. And they're actually considered an early sign. Even though we don't know whether this is going to occur or not, these changes are often an indicator of the beginning of a neurodegenerative disorder. The trigeminal nerve, on the other hand, the one that's sensory within the olfaction system, there is no evidence of loss of function, even though the background of exposures is the same. We see translocation, oxidative stress, systemic inflammation, abnormal detoxification according to genetics, same background, but with neurodegenerative disorders, we do not see any evidence of trigeminal nerve dysfunction. So this is just my image of what a nerve cell looks like. To give you an idea, you can see the nucleus and the main body of the cell, and all those kind of hairy parts coming off. And those are all ways that it is communicating with other cells, receiving messages. And then you go down the axon and you see the nerve endings at the end. And these are the other end of the nerve giving messages to other nerves that it is in close proximity to, but there are many nerve endings. So the amount of contact from one nerve cell to the other is multiple. The receptors, as I mentioned before, are part of that communication system. And you can see from this diagram that normally chemical messengers are very specific. It has to fit into the receptor just like a key in a lock, or a rocket ship from the planet going up to the space station, and has to lock in exactly. If it doesn't lock into a receptor, if it doesn't fit perfectly, as you can see on the right-hand side, no message is going to be imparted to the inside of the cell. However, there's a family of receptors called TRP receptors. I won't bore you with what that stands for. And they are polymodal, which means that they react to many messengers. There's many keys that fit. They react to multiple chemicals. They react to temperature changes. They react to oxidative stress. And they're widely expressed in the central nervous system. And they detect a wide spectrum of multiple chemical compounds, which can provoke sensory irritation, airway inflammation, oxidative stress. So we're going to talk about two members of this family called TRPV1 and TRPA1. These are the two that we are most concerned with respect to receiving messages and being stimulated from chemical exposures. These receptors are present in the innervation of the nasal lining. It's called the olfactory epithelium. It's where we smell things up in our sinuses. They aren't covered. So there's almost direct access from the chemical stimuli, the particulate matter, etc., when they enter into our nasal passages. They're activated by pollution, by oxidative stress, and systemic inflammation. I told you that, but it's important to remember this. They are involved in the development and perpetuation of chronic pain. So TRPV1 senses a lot of environmental pollutants, and you can see the list there. It's fairly extensive. They're programmed to respond to particulate matter pollution. They're sensitive to capsaicin, which is the ingredient in hot peppers, which makes them feel hot. The TRPA1 receptors are also robustly activated by multiple chemicals. I put in red the substance acrolein. It's ubiquitous. It's around in our environment all the time. It's formed during incomplete combustion of gasoline and oil, so it's a common pollutant. And I'm going to refer to it again later when I explain a bit more about these receptors. Repeated chronic activation of these receptors leads to upregulation and sensitization. Upregulation is when there's an increase in the number of receptors on the cell surface. So when there's exposure, the cellular response to that stimulation is enhanced. Sensitization refers more to an increase and a reduced threshold. So in other words, it will respond to some kind of stimulation, which could be noxious, or it could be a normal stimulation, but it's interpreted as noxious. It can be below the threshold to stimulate a response, but now it does. And the stimulation itself could be considered by anybody else or other cells to be innocuous, but not when there's sensitization. Another thing that's important to understand is that these two receptors often are co-localized, meaning they're on the cell membrane close to each other. We know that 97% of neurons that have TRPA1 receptors also have TRPV1. It's a little bit less for the TRPV1 receptors to have TRPA1, but they're very, very often occurring together on the same membrane and especially close together. And they actually can influence each other's sensitivity. They can sensitize each other. So an example is if you use acrylane, that substance I mentioned before from incomplete combustion of fossil fuels, you can sensitize TRPA1 receptors from repeated exposure. And when you do, you can sensitize TRPV1 receptors to capsaicin, the substance that gives the sensation of heat in hot peppers that TRPV1 receptors are programmed to respond to. So in fact, sensitization of each of these receptors is actually dependent on being co-expressed on the same neuron or close to each other. When they are upregulated and sensitized, they can also form a unit together. They actually join together, and it's called a TRPA1-V1 complex. And when they're like that, they're even more sensitive. That's when they interact in a synergistic, multiple type of fashion. When cells co-expressing these channels, these receptors are challenged with chemicals in the research laboratory, the TRPA1-V1 complex is much more commonly activated in comparison to either one of these receptors alone. So in other words, the more oxidative stress and systemic inflammation, the more we're going to see upregulation of these receptors in response. The more upregulation, the more they're going to be co-expressed, the more likely they will form complexes together, the more likely they become sensitized. And all of this amplifies the strength of the cellular response, how strongly the neurons respond, how long they respond before the messaging gets turned off, and the level of sensitization that they start to respond to lower levels of exposure to the stimulants. Sensitization to chemicals can occur without neurodegeneration, and it's common. For example, 1 out of 3 people with asthma complain of respiratory effects when they're near someone wearing a fragrance product. 1 out of 6 of them actually gets an asthma attack. People with migraines, up to 40% of people with chronic migraine report being triggered by chemical odors, especially scented products, perfume, cleaning products, and also gasoline products. There's this thing called central sensitization. It's defined as a state in which the brain, the central nervous system, amplifies sensory input from many organ systems. So it has an exaggerated response to information coming from the peripheral sensory system, especially chronic pain. And it involves the action of both TRPV1 and TRPA1 receptors. This is characterized by hyperalgesia, which means it's an increased response to painful stimulation. So you do something that's slightly painful, it will be an exaggerated response. The other characteristic is called allodynia, in which you perceive pain and in response to some kind of stimulation, which should not be painful, like a hug. It can be found clinically in fibromyalgia, which probably many of you have, and it's found in something called chronic nociceptive pain, which is there's no obvious injury or lesions that explain the pain. There's just this ache and pain. Chronic nociceptive pain and the cardinal features of central sensitization are commonly found in neurodegenerative disorders like Parkinson's, Alzheimer's disease, multiple sclerosis. You see this increased likelihood of chronic nociceptive pain. And the sensitization of the TRPV1 and TRPA1 receptors is evidenced by the hyperalgesia and allodynia that we can find in these patients clinically. They have reduced thresholds to pain, cold, and heat, especially those seen in Parkinson's. There are multiple central sensitization syndromes. They don't have to just be involved with pain. So you can become hypersensitive to other kinds of stimulation like light, electromagnetic phenomena, sounds, fragrances, skin irritants, bodily sensations, stress evoking life events. And examples are PTSD, post-traumatic stress disorder, restless leg syndrome. You can see the list here, but I point you in particular to those outlined in red: chronic fatigue syndrome, myalgic encephalomyelitis, and multiple chemical sensitivity. These are central sensitization syndromes as well. You probably all know this, but these are the case criteria to diagnose multiple chemical sensitivity. Symptoms are reproducible with repeated chemical exposures. The condition's chronic. Low levels of exposure, lower than were previously tolerated or commonly tolerated by others, result in the manifestations of symptoms. The symptoms improve or resolve when the incitants are removed. Responses occur to multiple chemically unrelated substances, and the symptoms involve multiple organ systems. Within the criteria, we note that the brain is the most common system involved. Some people have actually argued that the brain has to be involved as one of the systems in order to meet the criteria. We see that sense of smell is increased. There's a stronger sense of smell than others. There's a difficulty concentrating. People feel dull or groggy and spacey. We see oxidative stress and systemic inflammation in multiple chemical sensitivities, even if the detoxification system genetically is normal. We see problems in the blood-brain barrier. We see hyperreactivity of the TRP receptors in both the trigeminal and limbic system, which is nearly the brain that reads the information coming from the sensory system. What we do see is that the literature strongly suggests that people with MCS are more likely to have abnormal or different genes predisposing them to more difficulty in detoxification, especially detoxifying commonly encountered environmental chemicals. When we use a statistical method called regression analysis that tries to look for relationships, it's realized that MCS is a complex multifactorial disease. The genetic risk in chemical detoxification plays a necessary but not sufficient role in the root cause sensitization to chemical odors. In other words, if you don't detoxify very well, you're more likely to get MCS. Question: why do hot peppers burn? It's the capsaicin. It stimulates those sensors in the nervous system that sends a message to the brain of intense heat. We use this stuff in pepper sprays, bears, student riots in the United States. It's important to understand this concept. We know that if you inhale capsaicin, it'll make you cough. So it's used in studies of cough medicines, and it stimulates the TRPV1 receptors in the bronchial tubes to provoke the cough. These are the sensors that are also sensitive to chemicals, and MCS patients are hypersensitive to the inhalation of capsaicin. There were some studies done on perfume inhalation. The very first one was a small study in 1996. So these 9 people had at least a 2-year history of airway symptoms. They also had headache, fatigue, dizziness, and chest pain. So it was more than just the respiratory system. And these people alleged that the symptoms were induced by chemical odors like house paint and perfume. They did tests and they ruled out allergies and they ruled out asthma. There was nothing wrong with these people, but they got these symptoms with these exposures. So they were challenged with inhalation of perfume or salt water as a placebo. And they put a nasal clamp on the nose to prevent the detection of the scent of perfume. So they didn't know what they were being exposed to. And the provocation by perfume verified the complaints that symptoms were provoked by perfume inhalation. And the results were reproduced in these people when they did similar testing again at least a week later. So what was concluded was that the symptoms were not transmitted by the olfactory nerve because they couldn't detect the odor of the perfume, that it may have been induced by the trigeminal nerve in response by either the respiratory tract or maybe even the eyes. So the same group then tested a similar group of patients a couple of years later that had asthma-like symptoms that were provoked by multiple chemical exposures. Again, they ruled out asthma and allergies. The patients again had other symptoms from multiple systems, again, including eye irritation, fatigue, headache. And they postulated that the symptoms were induced by the trigeminal nerve. And so they did a capsaicin inhalation challenge. And the patients with chemical sensitivity with the asthma-like symptoms coughed more than the control group after capsaicin exposure. So this same group of researchers has produced multiple other papers since then with the same kind of thing. Respiratory symptoms plus symptoms from other systems, asthma ruled out, patients meet the criteria for MCS, and they all demonstrated respiratory sensory hyperreactivity due to the sensitization of TRPV1 receptors as demonstrated by the capsaicin challenge. When they followed up after 5 or even 10 years later, there was no reduction in the sensitivity to the inhaled capsaicin. One of the criticisms could be, yeah, well, these studies are coming from the same group of guys. Maybe somebody else should try and do that. And I have to tell you that similar findings have been published by other centers in Denmark and Japan. When we look at how the brain functions using brain scans, we find consistent evidence that people with MCS do not habituate, which means they don't get used to repeated sensory stimulation. If you've ever walked into a place and stayed for a while where it had been freshly painted before you had MCS, you tend to not notice the odor anymore after a while. You habituate. Chemically sensitive patients do not habituate. There's an altered processing of the information coming up from the sensory system into the brain. There's an overactivation in the limbic system. That's the part of the brain I mentioned before that responds to sensory information from the periphery. It's overactivated in response to a challenge. There are olfactory and cognitive changes associated with what they see in the functional brain scans when patients are challenged. There's differences in odor processing, including a prolonged recovery time after exposure. Patients with chemical sensitivities have a stronger sense of smell than others. And that's a subjective complaint. But a number of studies of people with MCS saying, can you detect an odor? Can you identify what the odor is differently than others? There's no evidence for olfactory nerve dysfunction. And this differs from neurodegeneration, but the discrepancy can be explained by the trigeminal sensory irritation. The two systems are linked. You can tell, and through memory and association, maybe even tell what it is, but where the sensitization is taking place is in the trigeminal nerve, not the olfactory nerve. We know from the brain imaging studies that there's stronger brain responses, that the perceived intensity and unpleasantness of the odors is significantly higher. And it's probably due because the odorants also stimulate the trigeminal nerve, and the capacity to detect these chemicals is mediated by both nervous systems, olfactory and trigeminal, and they mutually interact. So there's some other objective abnormalities found in MCS. People with MCS are more sensitive to noise. And there's been a finding of a change in a particular reflex, the medial or olivocochlear reflex. This is the reflex where you try and listen with one ear. For example, you're in a crowded restaurant and someone's talking to you, you tend to focus on the voice of the person you're listening to, and you turn off the noise coming from the rest of the restaurant in order to hear. And that's a reflex that we do without being consciously aware. That system, that reflex is impaired in MCS. There's also something called metabolomics, and this is something that uses all kinds of fancy things that I list here: analytical chemistry, platform technology, et cetera, and what it does is it analyzes tens to maybe several thousands of fine chemicals at a molecular level, but it can identify a pattern of these molecules in complex conditions. They've done this in all kinds of complex diseases. And there's been one study that I've been only able to read the abstract because it's written in Japanese, which has shown a biomarker pattern of the metabolome of thousands of chemicals that's unique for MCS. I show you this slide just to show you what strong scientific evidence means. It means that it's a well-designed study and there's a limit in the amount of bias that can perhaps affect the results wrongly. This is the opposite of what you'll see in a court of law, where the experts give opinions, where people who are judging you and your condition are considered experts. The other end of the spectrum, the top of the pyramid, systematic reviews and meta-analysis. Systematic reviews is done to answer specific questions that are asked before the examination of the research. It's transparent, so we know how the studies were found, how the studies that they're looking at are judged. So they do a comprehensive search. There's no bias for the selection. It's all identified beforehand. They rate the quality of each study and then come up with conclusions. Meta-analysis is just a statistical technique to try and combine data from different studies to see what the total amount of data actually says. And I told you this for a reason. When we look at systematic reviews and meta-analysis, we know that air pollution and neurodegenerative disorders are associated with Parkinson's disease, Alzheimer's, cognitive decline, and dementia. There are 6 systematic reviews of meta-analysis listed on this slide. When we look at systematic reviews for multiple chemical sensitivity, we know that the odors are processed differently by MCS patients compared to controls. We know that MCS patients have altered processing with overactivation in the limbic system and olfactory and cognitive manifestations as a result. Systematic reviews show the strength of these 2 points. So this summarizes neurodegeneration and compares it to multiple chemical sensitivity. We compare the associations. You can see pollution exposure, genotype for detoxification, oxidative stress, systemic inflammation, disruption of the blood-brain barrier, chronic pain, central sensitization, decreased cognition. They occur in both. When it comes to loss of brain mass, you see that in neurodegeneration, but you don't see it in chemical sensitivity. You see olfactory nerve dysfunction in neurodegeneration, but not in chemical sensitivity. Trigeminal nerve dysfunction in chemical sensitivity. We see upregulation of the TRPV1 and TRPA1 in neurodegeneration. That term has not been used to describe chemical sensitivities, but we do have evidence from the challenge studies that we have TRPV1 sensitization, TRPA1 sensitization in chemical sensitivities, but we don't have that evidence in neurodegeneration. How many Canadians are affected? You can see from this slide that way more people are affected with chemical sensitivities than the other common neurodegenerative disorders, even combined. And I tell you this because you need to understand that there's very little funding for research for chemical sensitivities. The total funding for the 3 conditions, MECFS, fibro, and chemical sensitivities, was $1.8 million. It's 4% of the funding in research in Parkinson's disease. It's 2% of the funding for research in Alzheimer's disease. There were 13 studies funded, 11 fibromyalgia, 2 for MECFS, and none for chemical sensitivities. So to summarize, there's a strong overlap of the mechanisms associated with environmental exposures between neurodegeneration and chemical sensitivities. And this includes the genotype for detoxification, oxidative stress, systemic inflammation, disruption of the blood-brain barrier, chronic pain, central sensitization, decreased cognition, involvement of the TRPV1 and TRPA1 receptors. I want to mention neurodevelopmental disorders. These are things that occur to young children when the brain is still developing. In particular, autistic spectrum disorder, oxidative stress and systemic inflammation is seen in ASD. It correlates with how severe the autism is. Adults with ASD, autistic spectrum disorder, may have an increased sensitivity to fragrance products. They get respiratory symptoms, migraine headaches. Individuals who are relatively high functioning show decreased neural habituation, increased responses to repeated consistent stimulation. But on the other hand, when the autistic spectrum disorder is really severe, they're more likely to have a reduced sense of smell, greater evidence of damage. What's interesting is that mothers with MCS are more likely to have a child with autistic spectrum disorder. A systematic review has shown an association between autistic spectrum disorder and detoxification genotype abnormalities. As was mentioned at the beginning with that, when I was introduced, I was a clinician member of the Task Force for Environmental Health in Ontario. The interim report was entitled Time for Leadership, Recognizing and Improving Care for Those with ME/CFS, Fibro, and Chemical Sensitivities. The final report came out in December 2018, called Care Now, an action plan to improve care for people with these three conditions. So it's time for a Center of Excellence for Environmental Health. And this was the recommendation number 8 by that Ontario Task Force. We need to create a Center of Excellence responsible for care, education, and research in the three conditions, ME/CFS, Fibro, and chemical sensitivities. Now is the time. Thank you.